guess I'm gonna get started. But if you...
We should set up a lecture page.
Eventually, I just got to the point where I could tune it out. But then it's bad because if they actually call my name,
Hello, everybody. Thank you for coming. We're just gonna take a minute to make sure the lecture recording is set up, so that you and your classmates can take this later. Although it does seem like it's recorded.
Oh, yeah, then we're good. Yeah.
So we'll just get started.
Woo!
Sorry, you have to be here with us on this beautiful day.
Do you want a microphone?
Yeah.
Thanks.
Oh.
Welcome. Oh! Guys are like the Beatles. You're Paul.
That's it.
That's it.
Hello?
I'm not Paul.
Hello. Hey. Hello.
Do you have it set up here? Try a different one. That one might not have been charging. Is it on? Try that one.
Oh.
Oh, there we go.
Okay. Huh?
Rally up.
Can you hear me? It's fine. Oh.
The small screen should be up.
Yeah. Yeah. No. We are on it. But why isn't it on?
Is it on?
Yes.
Try laptop too.
That's what I just did.
Should be laptop one.
Plugged into. Yeah.
Do you want to try just HDMI into mine to see whether it's the connector?
Yeah, we can use yours if we want.
Or we can just see if
We can just AirPlay.
Oh, yeah, do that.
Maybe.
There it is.
All right. So again, thank you for coming. I hope you can hear me. So today, I'm Oliver. If you don't know me, we have Faye, Wenyi, and Paul here, and we're going to try to walk through as much of the material from the second half of the semester as we can. The idea is that we're going to be focused on problem solving. I'm not going to try to re-lecture at you. If you have conceptual questions, please ask, but for the most part, we'll be doing problems. Does anyone have logistical questions before we start? Yeah. We will put the slides up on Canvas.
Do that right now.
We're doing it. Is there a question over here? Okay, great. Yeah, we're going to maybe we'll post them on Piazza. There'll be a link on Piazza. Also, maybe on that same Piazza post, if y'all want to post questions on that, we can monitor that and respond if you don't want to raise your hand or if you don't think you have time. Okay. If that is all, then we'll get to it. So this is what we used for, these slides are what we used for last fall, in which we did strings on the midterm. We did not do strings on our midterm this semester, so we will also be talking about that very shortly. But there's not a whole lot to say about it, so I'm just going to tell you. Okay. All right, yeah, so for strings, we're not looking for you to know like the implementation details of equals equals defined on string objects. We're not looking for you to know like how certain string functions work. What we do want you to know is what Robin Karp fingerprints are, why they're useful, why we would use them, how you compute them, and yeah, I think that's about it. I mean, really, like, think of Robin Karp as just, normally we use it as a soft way to introduce you to hashing before we introduce you to hashing, so we can ask you questions about it on the midterm, but we didn't do that this time. So as long as you understand what Robin Karp is, how to compute it, I think you'll be all right. Does everyone remember what Robin Karp is? Okay. So Robin Karp is an algorithm that essentially takes a string and turns it into a number. So it's just like a hashing algorithm. We have a string of ASCII characters, and we just want to find some way to turn that string into a number, resulting in the fewest possible collisions with any other string, right? So you want to make this, like, you want your algorithm to be fairly complex. We're not looking for something, you know, everyone has seen the example a million times. This is a bad fingerprinting scheme. Yeah, so it still is just a way to turn your string object into a number, and we're trying to minimize collisions. I would suggest going back and looking at the slides about it. Any other questions on Robin Karp? Yeah.
What does that say on the board?
Can you read that better?
Yeah.
Okay. It's s at 0 minus a, assuming that s is a string. So you're subtracting off. Yeah, you got it. Okay. Can everyone read this? Are there like more lights we can use? Okay, whatever. Does that help? Yes. Okay. Great. All right. With that, we'll move on to hash tables. Jake, are you doing any of them? You haven't signed it. Okay. All right. So we're going to talk a bit about hash tables and collisions. We're going to do a couple problems relating to hashing. So one thing that we really want you to be aware of is when we have a good hashing algorithm, why we would want a hash table for something. It's really important to know, like, sure, it's really easy to just always say, like, oh, I need to store some data, let's throw it in a hash table. But that's not the smartest way to go about things. So we want you to think about, why do we want to use hash tables, and what situations do we want to use hash tables? So can anyone tell me why I may or may not want to use a hash table for a mapping between the numbers 0 to n and some set of objects? Arbitrary data. Yeah.
If you're just hashing 0 to n, then the vector is both faster and more space efficient.
Yeah, we already have a vector. That's what a vector does. Right, exactly. So if you're mapping some small range of the natural numbers onto some set of objects, you don't need a hash table for that. It's not doing anything for you. Can anyone tell me a situation in which you would want a hash table? Emma? Okay. I get fast insertion and pretty good search on a vector, right? What sort of keys do I want? Yeah, strings, large numbers, some data that it doesn't make sense to throw into a vector. Okay, good. All right, so what are hash tables bad for? They're bad for anything that you need some relation between the data, right? We don't have, think about how a hash table is implemented in C++. All of the data structures that are associated with, that use hash tables as their underlying data structure are called unordered. That should give you an indication that you don't want to be using these things for any sort of data storage where you're thinking about relations between those objects. If you need to find which objects are less than another one, you have to do a linear search on the hash table, which is bad. So for something like that, what's a great data structure to use when we're looking for data that is less than a certain value? Yeah.
Binary search tree.
Yeah. BST, AVL tree are great options because we can go find where that value would be, and then everything to the left or to the right of that is going to be the data we want. Okay. We have a few methods for handling collisions. Someone quickly explain to me what separate chaining is? No one learned what separate chaining is. Yeah.
It's a form of direct addressing where you take a hashing compression value and you insert the key into some sort of data structure that's at that hash value, whether it's a linked list or an AVL tree or whatever.
Great, yeah. So we have our array that underlies our hash table. We hash into a certain address into the array, and whether or not there's data already there, we just throw it into some data structure, the root of which is at that address in the array. Right? Most of the time in lecture and lab, we talked about this being a linked list. That's a fine example. There was a written question a couple semesters ago on implementing an AVL tree inside of that. So think about different types of data structures that you can use with separate chaining. And then for open addressing, can someone just explain to me why we need to think about these collision resolution methods with open addressing?
Whenever you encounter a collision, you just move to another address and see whether or not it's open or not.
Yeah, exactly. So we don't have these data structures hanging off our array anymore. So now we're looking at if we collide with something in our data array, we now have to find another place to put it. And we don't want to just choose randomly because we have to go find it again at some point in the future. So we want to have some algorithmic sense in understanding like why or where we're going to put something if it collides. Good? So linear probing, quadratic probing, and double hashing are all methods to do this. I trust that you know what they are. Linear probing and quadratic probing, very likely to show up on the exam. Double hashing is less likely just because it's a little more complicated and takes more time. But definitely know how it works. These bullet points, I mean, really all of these should probably be on your note sheet because that's not something that we would give you on the exam. Okay. So now we have a question. This is very similar to what you'll see on the exam. So we have a hash table storing keys, and it handles collisions with double hashing. Here's our double hashing function. We're going to insert some values. What is the index of one of the values? I'll give you a few minutes to talk amongst yourselves and do it. And then we'll come back and do it together.
Yeah, for
Well, let's see if I can get any of the problems right.
Too much to expect.
Huh? All right, yeah. Just come stand up here with me and be like, that's not right. What? You're probably that'll be a good time.
Oh, sorry. So you just select that link, same number, and
I just don't think that will. Yeah. Alright, I got you. Actually, I should probably also just do that because that's way easier.
All right. Are you all still working? Would you like another minute or? All right, I'll just start, and then if you're still working, that's fine. I'm just going to do it on the board because Faye didn't tell me she had her iPad. Okay, so I like to set these problems up and like do the whole thing explicitly because then I feel better about myself. But so here I have my array, I have the numbers I'm going to insert into my hash table, and I have my two functions that are governing collision resolution. So let's insert the first one, 35. 35 mod 11 is 2. So I'm going to insert it at 2. Are we good with that? Okay. All right. 22. Where does 22 go? Nice, Joseph. Yeah. Okay. 44. Also here. Okay, so now we have collision. So our double hashing method is T of k plus I times T prime of k for I equals 0 to m. Okay, so let's just write it out. T of k here is 0. T prime of k is k mod 7. So that should also be 2, right? Good. So this is 2. 7 minus 2 is 5. So down here I have 0 plus, initially you do 0. You can just start at 1 because you know that 0 is never going to work. So now we have 0 plus 5 gives us 5. So I'm going to put 44 there. Okay. 59 is 4 mod 11. Put it in. And 33 ends up going to 0 again, right? So we're just going to calculate that. So this is 0. K mod 7 is 5. So we have 7 minus 5, which is 2. Now we have T of k is 0 plus 2, puts us where 35 would be. So let's do 0 plus 4, which would put us where 59 is. We can do 0 plus 6, and that's where we'll put it. Okay. Does anyone have any questions about that? Great. Yeah. T of k plus I times T prime of k. T prime of k, well, we'd give it to you in a problem. Yeah. Yeah. Pratik?
So in the T prime k, on those slides it says like T of k mod 2. But on the next slide it says k mod 7.
Yeah. So I think this is a potential T prime. And this is the T prime for this question. Does that make sense?
So we'd be given.
You will very explicitly be given the double hashing function, both of the hashing functions, if there's a double hashing problem. Yeah. Yep. Definitely just do what it, just do what it says. Okay. Any other questions on this? Cool. All right. Yeah, I guess I didn't really have to try that hard. Okay. Which of the following are invalid hash functions for a hash table of size m? Any thoughts? Yeah.
The first one is invalid because it's not deterministic.
Yep. Right. Why is that bad? Right. Yeah, if I was trying to find 33 again and it was randomly placed in my array, how am I supposed to go get it? Yeah, so 1 is wrong. Yeah. Yeah, exactly. We still have to be able to fit it inside of the array. If m is 10, then multiplying something by 503 is almost guaranteed going to put it outside of, I think, unless it's 0, is guaranteed to put it outside, right? So 1 and 2 are both wrong. Someone argue to me why 3 is okay? Yeah.
Because if you run it on the same key value, you'll get the same exact hash value.
Great. And if always fits inside of our array because we have mod m at the end. All right. Cool. Does anyone have any more questions on hashing, collision resolution? I'm happy to answer conceptual questions. Yeah.
In lecture, I thought the hashing function was just something that makes a unique-ish number, and then you have to mod that yourself for the table. This, the definition of the exam going to be this one.
Yeah. I think that might actually be a problem with the way this question is written. You're right. A hashing function, right. So a hashing function should be independent of the size of the hash table. I guess here we're asking for which of the following produces a valid index, which is not what the question asks, which is confusing. But that's the way I answered it. And that is the way that whoever wrote these slides answered it. So yeah, that is true. A hashing function is independent of the size of the hash table, and that is the definition you should use for the exam. Thank you. Anything else? Y'all are good on hash tables? Okay, you will notice that we only did an example on double hashing. If I were in this review session, I would suspect that means that I should probably do linear probing and quadratic probing on my own, because those will probably show up on the exam. All right, we're going to move on to trees and tree algorithms. Here are two definitions we have about trees. A complete tree is a tree is binary, right? The binary heap. A complete tree is not binary. The binary heap is a complete tree, right? Someone explain to me why we make the binary heap a complete tree. Exactly. There's this really convenient property with complete trees that we can take that tree structure and put it into an array, which is a much more efficient representation of the data. And that's so usually when you're talking about complete trees, we're looking at trees in arrays. A full or proper tree means every node has either 0 or 2 children. Just a definition. We have a bunch of traversals that we did for several weeks in the second part of the semester. Level order should be very simple. The other three, I think if you do a couple examples on your own, you should get a handle pretty quickly. Most likely, a question where we give you a tree and we ask for the traversal of it is like, that's a very easy question. We'll probably expect questions that are, we give you 2 traversals and we ask you to build the tree and give us the third, something like that. Okay. We're going to do a couple examples, so I'm just going to keep going. All right. Can someone read the code and then tell me what are the worst case complexities of the find and the insert operations? I think it says find 281 and insert 376, but it should be 280 and 281, like in the code. What are the worst case complexities? Someone else. Yeah. Why log n?
For finding insert, because when we go by the height,
Do we have any guarantee on the height of the tree?
it's worst case O of n if we have a stick tree.
Yeah. Yeah. So the important point here is that if we don't give you a guarantee on the height of the tree, if we don't explicitly say the height of the tree, or if it's an AVL tree, you know the worst case height, right? So if we don't give you either of those 2 things, then the worst case for all of these operations will always be O of n, because now you're looking at just always assume that it's a stick, basically. And what is the complexity of finding or inserting onto the end of the stick? OK. All right. Here's a tree. It says preorder, but I promise you the next 6 slides or whatever are the preorder, in order, and post order. So go ahead and do those. Yeah. Average case? Well, there's no average case because that code is, like, that's the code, right? So, I mean, it says worst case, but, like, what is the complexity of that operation? Yeah. I think average case on a BST is usually log n. Anybody? Hello? Average case on BST is log n? Yeah. OK. So in general, yeah, average case is log n. All right. So here's a tree. Go ahead and do pre-order, in order, and post order. And then we'll do them together.
Don't screw everyone up. I still. Huh? It was an LBME, so like not even students wanted to drop in. All right.
Okay. We're good? Cool. Let's do them together really quickly, and then we can move on, because we don't like trees. All right, preorder. I have it written on the board. What is the order of preorder? Not like, I'm sorry, not the sequence, but just what is like if I have a small subtree. Yeah. Middle, left, right. Yeah, thank you. So with preorder, you can think about when you first, like if you're tracing out the traversal or whatever, when you first go to the node, that's when you visit it or like print out the data inside or whatever. So let's do that one. What is like the really crucial thing about preorder? How does the structure tell us how to build the tree? Yeah. The root is always the first node. So 9. All right. I'm just going to do it because I assume that y'all have done it. But all right, so it should be 9, and then we're going to go left. So I'm going to go to 4, and then 3. Now I go right from 4. I go to 6, 5, and 7. Then I'm going to go right from 9, go to 17. There's nothing to the left, so I go to the right. 22 and 20. Good? Okay. How about in order? Let's say I have just 3 nodes. What's the order that I visit them in? It's literally on the board. I will stand here all day. Yes? Thank you. Okay, and so given that that is the case, what about the structure of in order helps us out when we're trying to build a tree? Okay, well that's, yeah. That's a good point. But we know that if we know where the root is in the in order of any subtree, then we know everything to the left of that is to the left in the actual tree, and everything to the right is in the right of the actual tree. Okay, so this does happen to be a BST, so you could just write it out in sorted order. I'll actually do the traversal, but okay. So you go all the way left, so 3. Then we visit the middle, 4. We go right, but then that node has a left child, so we come down. 5, visit the middle. 6, go to the right. 7. Now we visit the root at 9. We go right. There's nothing to the left, so we visit that node. Now we go to the right. There is something to the left, so we visit that node. And then finally, visit 22. Okay, for post order, what is the order? Yeah. Great. And so what does that tell us about where do we know the root is? What? Yeah, it's the very last piece of data. All right, so post order. We're going to go all the way to the left again. 3. We come up, we go to the right. Go all the way down. 5, 7. And then I think about, like, I get to the leaves of a tree, and then you start, like, bubbling back up, I think is one way to think about it. So you go to 7, and then you're at the leaf, and now you can come back up to 6 and 4. Now we'll go to the right, and we'll come all the way down to 20, and then 22, 17, and finally 9. Okay. So very likely there will be a question where we give you 2 out of the 3 of these, and you have to build the tree. I say very likely. I wrote the tree questions, so I feel like I have a lot of authority on this. So that is something that I would practice. Just take 2 of these and try to build the tree. See where you come up with the post order. Yeah. It is possible. If you don't have the in order, there are cases in which you will not have a unique tree. So think about how that might affect how we would ask you a question. Yeah. Okay. I think there's an example of that in a couple slides, so we'll do one together. All right. Here's a question just about the structure of the tree. We want to know between complete, proper, and balanced, which properties does this tree have? So can anyone give me one? Yeah. It is not complete. Why? Yeah, 11 and 14 are not. The tree isn't being filled in left to right. If I moved 11 and 14 to be the children of 2, it would then be a complete tree. Okay, great. Is the tree proper? I don't know if you went over the definition in lecture. Someone else. Yes?
Yes, because each leaf has 0 or 2 children.
Yes, but I guess, yeah. So leaves are every node. Every node in the tree has either 0 or 2 children. Yeah. Okay, and is the tree balanced? You think yes? Great. Yeah, I think you're right. Yeah, so my idea when I think about is a tree balanced, I have a really hard time remembering like which side is supposed to be negative or positive. Maybe I'm dyslexic, but I just like for every subtree, so I'd start at the bottom, I'd look at 13, and I'd see what's the height on the right, what's the height on the left, like the maximum height, and then do those differ by more than 1? And that's an easy way to see if it's balanced or not, I think. So 13 is balanced. 10 has 2 on the right and 1 on the left, so it's balanced. 15 has 3 on the left and 2 on the right, so it's balanced as well. Okay. Any questions? All right, just like I said. So I'll give you a few minutes to do that, and then we'll do it together.
What did you learn at 376? I don't.
Maybe I don't remember what we covered.
We're doing as part of the distributed.
That's why I cut out this like blue slides. Yeah, all those. Yeah. But this is like lecture 2 that I ran to go before.
Because all those people, that's where you started. Is there anything else that's still not
So you're doing great.
At least every topic that Chris was is covered.
So who can tell me one thing about the resulting tree without doing any work? Yeah. Great. Who can tell me another thing? Requiring just by looking at the traversals. Yeah. Yeah, it's a BST because the in order is the sorted data. Right? So we already know where the root is, and we know that it's a BST. So it's a lot of good information. All right, so we know what the root is. So we know 5 is our root. Then we can go look in the in order. 5 is our root. What do I know about 1, 2, 3, and 4? They're on the left, right. So I'm going to have 5, and then over here I'm going to have 1, 2, 3, and 4. And here I'm going to have 6, 7, 8. Good? All right, so now we can just play like mental recursion and my favorite game. Sorry. Okay. So what do we know about, given that the post order of the left side is 2, 1, 4, 3, what does that tell us about the structure of the left side? Yeah. Its root is 3. Great. Okay. So now, what else can I say about the left side of the tree? Yeah. Four on the right side. Yep, looks good to me. 4 is our right. And then how are 1 and 2 going to be structured on the left? Yeah. 1 will be the parent. That is true. And then where will 2 be? Someone who has not answered yet. Yeah. Yeah. Why? Yeah, exactly. If it was to the left, then we'd expect to see it on the left. Also, we know it's a BST, right? So, like, it better be like a BST. I don't know how to say that better. All right, what do I know about the right side of the tree? Pratik.
You know that the root is
Do I know the root of 7? Post order? I know my root is 8. All right. And then how are 6 and 7 going to be structured? What's at least, someone tell me just which side they might be on. They're to the left. Great. Because in the in order, they're both to the left of 8. All right. And now we can go back to the post order. 7 comes before 6. What does this mean? 6. And then where is 7 going to be? On the right. Cool. Does anyone have any questions about what I just did? Where 8 was? So I know that 5 is my root, right? So I can split off this. And then given that I know that these 3 are in 1, I can come back here. 8 is the last node in the subtree. So it's the root. Does that make sense? It's the same thing that you do. Like you can imagine just taking that subtree and taking those traversals, 6, 7, 8. And then you can just imagine like you're starting fresh, right? Yeah. Okay. Any more questions about building trees? Great. We did it. Okay, AVL trees. What is a problem that you're likely to see come up about AVL trees? Yeah.
Rebalancing, rotations.
Yeah, for sure. We're probably not going to give you a like build a tree where it's an AVL tree because it'd be easy. But for sure, there will be questions about how many rotations does it take to get here or to make it balanced? Or if I insert all these nodes or all this data, how many rotations does it take to get to a balance point? So we'll do a couple of those. All right. Here's some stuff about AVL trees. I assume you know it. Great. So here's a question. You should go ahead and try it for a couple minutes, and we'll do it together. We have a tree. After inserting 14 and performing all the necessary rotations, what would be the resulting preorder traversal?
Yeah, there's a lot of information.
Find out.
You're not. Example, right?
All right. Is everyone, do y'all want another minute? All right, I'll take that as a no, I guess. All right, someone tell me where 14 is going to go? No. Someone else. Yeah. I'm sorry, what? To the right of 13. Yeah, great. So we know it's greater than 10, it's greater than 12, it's less than 16, it's greater than 13. I'm going to put it here. All right. What is the problem? Yeah. 16 is unbalanced. Yeah. So you can think about it the load factor way. Again, I'd just say like 2 over here and 0 over here. Absolute difference is 2. So that's bigger than 1. All right. Someone tell me how I rotate this thing to make this work out. Yeah. Okay. And then what happens? Okay. Great. Good? Does everyone understand the double rotation? All right. Cool. After this class, you'll never have to worry about it again. And your lives will be easier. So is this good? Are we done with rotating? Okay, great. I think we're done with rotating. So now all that's left is to take the preorder, which I'm going to say is 10. Sorry, I'll bring it over here. 10, 5, 3, 1, 8, 7, 12, 11, 14, 13, 16. Good? Any questions on this? All right, moving on. Yay. All right, so now what if the node 10 was then deleted? I don't know what 14 is still removed is supposed to mean. Hey, Faye, do you think that means that we just start with the original tree? All right. Okay, so do that.
Yeah.
Thank you.
Also, you want to use successor.
Okay. Thank you. It's confusing. It says was then deleted. Like it's part of the chronology of the problem, but it's not.
Yeah, also the slides that we have 14 is still removed in parentheses and then the question mark outside of it on the next slide, which makes more sense than 14 is still removed.
Maybe.
You tell me.
Yeah. Good question. Yeah. What's your name? Dustin asks an important question that you need to know. Are you supposed to use the in order predecessor or successor? And I believe it's successor for this question. We didn't specify it, but we would have to. Or we would take both responses. I'll do them all. Huh? I'd be kind of stoked at teaching electric.
You could.
I could. If I got a PhD. Oh, you want it. But it's gonna happen. I like your vibe.
Step one, you gotta want it. It's just the truth. Oh my gosh. That's gnarly. Do you know how hard
Dustin, what's the in order successor of 10? All right, cool. So, someone tell me why I need an in order successor? Yeah. Yeah.
You want to keep the BST invariant like true, so just grab something that's closest to the root.
Yeah.
So that you
Great. Yep. So I just need something that still fits with it. You could like think of those three elements as a bucket. If you remove one, you can replace it with any of the others. Okay, cool. How do I find the in order successor? Dustin. How about predecessor? Yep. So we're looking at an AVL tree, anything with a BST invariant. You can also, like, if you can just look at all the elements, you could say, like, you know it has to be the greatest element smaller than the root. But that's like the algorithmic way to get there, which is what you should know. OK, so we're going to use successor. So I'm going to replace it with 11. Because I go right, go all the way left. I find 11. All right. What's the problem? It's not balanced. Good job. All right. What do I need to do to balance it? I can just do all the problems myself, but I feel like that's not fun. Yeah. I want to rotate 12 left. OK. How do I... what do I need to do before I can do that? Like I want to reorder this subtree, right? Yeah. Okay, good? This is what you're saying? Cool. Yes, so we need a double rotation. We can't just flip 12 over because it won't do anything for us. So we're going to double rotate. I'm going to put 13 on top. Okay. Are we good? Yeah. What? 13, 12. How did I get here? So we had 12, 16, 13. And then from here we got 12, 13, 16, right? Does this part make sense? Okay, and then I just want to do, because this is still unbalanced, so I just want to rotate left on that. The double rotation is going, so this is the single and then the double. Yeah, yeah. Good question. Yeah?
When you're deleting a node from an AVL tree, are you technically just swapping the two and then deleting it and fixing up, or are you just replacing it and then fixing down?
I haven't thought about it in terms of fixing up and fixing down. I don't think it makes as much sense because it's not a heap.
Well, I mean more like in terms of the algorithmic sense of what you're doing in terms of the structure itself. Are you when you end up deleting 10 from the AVL tree, where do you start checking the imbalance?
Yeah, so you always want to start at the bottom. Because if you find that the root is unbalanced, that's like the worst thing to do, right? Like you don't want to start like rotating the root because it's going to be a huge pain. So yeah, definitely start at the bottom and work your way up. Yeah?
Just to clarify, like an implementation, like a recursive implementation, it would be like calculating all the balance factors as the recursion unfolds, right?
Yeah, you could do it that way.
Yeah, it would be like we recursively get to the 10, delete it, and then add some unfolds.
Yeah, that would be fine. Yeah. If we chose 8 as our new root, so if we chose like the in-order predecessor instead, I think 7 would just hop up in its place. So we'd get 7, and then 8 would be up here. Yeah. I do wonder. I think, well, if there's a right child, then you'd be using that node. So. Yeah, good question. All right, I'm going to skip the traversal because I think that y'all can do it. All right. Faye, is this a continuation, or do I start from the? Okay, cool. So now we're going to delete 13 from this tree. All right, so we're going to continue to use in-order successor, I believe. So what happens? I'm going to delete 13. What does it get replaced by? 16. Okay. Is this balanced? Looks good to me. Cool. And then, why does it, what the?
Well,
All right.
I think that's probably fine.
Yeah. Okay, so it's trying to get us to rotate on the root, which we can do. All right, so we delete that, and now, what's our problem now? Yeah, we're imbalanced. Okay, how are we going to fix this? Rotate right on the root. Yeah. Okay. So what's my new root going to be? 5. Okay. And what is 5's right child? Good. And this is preserved. what is 11's left child? 8. And 8's going to keep 7. And then we get 3 and 1. Are we good? Does anyone have any questions about how that just happened? Yes. So we know that there's an imbalance here, right? Because we have 1 on the right side and 3 on the left. So we're going to have to flip the left side over. So we know that 5 is going to be our new root because it's the left child. So we can put that here. Now, 5's right child we know is going to be 11 because that's what it's still connected to. 16 will still be 11's right child. We're not changing anything to do with that. But 5 has a right child, which is problematic because 5 is also going to have 11 as its right child. So we just need to flip 8 over to be 11's left child. Yeah. The new left child, the previous left child. Yeah, if your new root, like you can think about it in the sense that like 5 is going to be our root, and then both 11, like it already has a right child, and now 11 would also be its right child. So you just have to figure out what you want to do with one of the children. And to keep the BST invariant, that's what happens. Yeah. A double rotation on the root. I guess if you had like, what could 7.5 here, and then if you had 14. Yeah. I don't know if I can come up with an example right now, but I mean, you would just, it's the same thing, yeah.
Yeah, you just have to rotate the
Yeah. Yeah, just think about it in terms of subtrees and then like, yeah. Okay, good. That's it for me. I'm sure you're tired of hearing me talk. Paul's going to come up and talk to you about the graph ADT. Remember to use for loops on the exam instead of while loops. I don't know. Ternary operators.
So you just flick this thing back. That's all. All right. I see.
There's a standby setting that you might be on. You're good to switch.
So, okay.
One rotate, is that right? Yeah. Okay. So like, is that once we excuse me? Once we remove the node, is that like guaranteed with
You're ready to roll.
2 rotations at most?
Yeah, I think we could set that up, but we'll just roll with it. If that's cool.
Okay.
Oh, yeah.
Okay.
You're just removing a single node.
I usually
That also should be 2.
Yeah.
And also, will you guys ask me a question like write syntax or C++ opposed to implement like just Make it balance, like balance the AVL trees.
I mean, balancing is pretty involved. We already had to do that.
Yeah.
That's probably be too much.
All right, guys. So let's get started on our next topic here. I'm Paul, and I'll be talking to you today about graphs and some graph algorithms. So we'll get started with a good practice question that transitions nicely from trees. So trees can technically be considered graphs with the following properties. So which of these can be true? Dense, cyclic, or connected? So let's think about this. Anyone want to help me? Yes, just connected. So for dense, this is not true. For any tree with v vertices, we always have a property of there being exactly v minus 1 edges. So a tree, no matter what, is always going to be sparse. And the same thing for cyclic too. A tree is actually, I don't like the wording of this question here actually. A tree is always just a graph. It's not technically considered a graph. A tree is just a graph that is both acyclic and connected. So those two properties alone will make a graph a tree. And then it not being dense, it being sparse follows from those. So C is our correct answer. The only thing here is connected. Now looking at this question here, using this adjacency matrix for a graph, we want to look at a potential DFS path through this graph and what could be a valid one. When looking at this, the important thing to remember about DFS versus other graph traversals is that whenever we're at a certain node, we always want to visit one of that node's children before any of its siblings. Okay? If there's any children that have been unvisited, we always go to that one next. And that is kind of the key to approaching this problem here. So we're going to be starting on vertex here 1, because that's what the problem specifies. And for these, I think whenever you're given one of the representations like an adjacency matrix or an adjacency list on the exam, it helps so much to actually draw out the graph, especially something as small as this with only 6 vertices. Visualizing the graph on paper really helps to go through this problem a lot more. It makes it a lot simpler. So we're going to do that. We'll notice all of the questions here. They start on vertex 1. And then we can either go to vertex 2 or vertex 3. Of our options. So let's start with drawing our graph. We're at 1. And looking in this row right here, all of V1's children, we see that V1 is is adjacent to 2, 3, and 5. Okay. So we want to mark vertex 1 is being visited. And now we can either visit 2 or 3. So far all of our possible answers are correct. We can go to either 2 or 3. It doesn't matter. So we'll look at the first ones with 2 or 3. With going to 2. So if we visit vertex 2, okay. Now we're right here on vertex 2. 2 and 1 have been visited. And now between A and B, our answers here, the options are between going to 3 or 4 next. And we can see that A is going to be invalid because on a DFS, we always want to go to one of 2's children next. Since we're at 2, we can see 2 from our adjacency matrix here has 4 as a child. If we're at 2, a DFS would always go to 4 next, okay? Because we want to jump down to 2's children before going to any of the previous siblings. If this question was asking about a possible BFS breadth first search path, then going 1, 2, 3, totally valid. It's fine. So we can kind of cross out A right there as being anything good. So going from 1, 2, and now to 4, because that's our only option, we'll continue exploring if V is a good answer. So we're at 4. We're going to mark it as visited. I'll highlight the little number there. We see that 4 is adjacent to 2 and 5. So we can draw an edge to mark 4 to 5. And now 5 is the only neighbor of it that has not been visited. So we'll go to 5 next. Okay, and that's keeping up with an answer consistent in B. We're going from 4 to 5. And looking at 5, 5 is adjacent to 3 and 6. So 6 hasn't been drawn yet. So now that we're at 5 here, going to 6 or to 3, either is a good option, but in this case, in B, it starts with 6. So B is a valid DFS because we went through each node and always went to the child of the one that we're currently at before looking at any siblings. So looking real quickly at like why C would be a bad DFS for this. So C is starting at V1, and then it's going to V3, and then we go to V5 and visit that. But then it's saying go to V2. But there's no connection from V5 to V2. And since we're at 5, we have children of 5, which are still unvisited. So if we went 1, 3, 5 in this DFS traversal, 6 would be the next correct vertex to go to. So that is not using the C. This traversal is not using DFS there. Good question. So yes, actually, so once we're at 5, we can go to either 4 or 6. Good question. Good. It doesn't matter the order of which child we go to next. So if we're going from 1, 3, 5, and 5 is our current vertex, sorry, I accidentally erased that edge. We have 2 options. We can either go to 4 or to 6. It doesn't matter. But we definitely can't go to 2, and that's why C is wrong. Well, let's draw it out. 1, 3, 6, and then you said?
5, 4, 2.
So far, 1, 3, 6 is good. We can go to 5, 4, and then 2. Yeah, that's correct. And that's just because we go from 1 to 3 and 5. We're following these paths directly. We're always going to the child of whatever node we're currently at. Is that part making sense?
Can you explain what you mean by child? Because I thought it was unlisted.
Okay. Yes. So child or a neighbor. I guess, yeah, in a terminology, in an undirected, it's not technically children because we can go both ways. But by child, I did mean neighbor. So when we're at 5, its unvisited neighbors are 4 and 6. So we can go to those next.
How will you solve this question if you want to use a graph or search?
All right, good question. How would this question look different if we wanted to use breadth first search? So since we're starting at V1, so we have, from V1, we have neighbors of 2, 3, and 5. So in breadth first search, this is where we have a queue, okay? And we're starting at 1, and then we push all of its neighbors into a queue, and then we proceed to visit the rest of those in the queue. So breadth first search that's valid could go 1 to 2, and then 2, 3, 5. So we would visit 1 and then 2, 3, 5 in any of those orders, okay? But the second, third, and fourth nodes that we visit has to be either 2, 3, or 5. So a stack would provide us with a depth first search because it does have to be a queue because if we draw a little queue here and we add 1, so let this be the back, this will be the front. If we start with 1 and we add it, we add all of its neighbors into this queue. So this would be 2, 3, and 5. And as we pop 1 from it, we want to make sure that those are the next. So in a BFS, 2, 3, and 5 have to be the next nodes that we visit for all 3 of those. Okay? Because we're going 1 level at a time. Whereas if we use the stack, a stack would provide us with a depth first search. So we could push 1 in. So we'd push 1 in, and this is with a stack here. We could go to 2 next. And then as we pop off 2, 2 would then push in its neighbors, 4. So 4 would come off. Here, excuse me, let me do a full. So we would start with 1. We would push on 2, 3, 5. The next thing coming off the stack would be 5. And then we would add 5's neighbors, 6 and 4. And then 6 and 4 would be the next things coming out. So that would naturally provide a depth first search there instead. So it does have to be a queue.
So for a graph, I guess I'm confused how we define depth.
So for a graph, it is a little trickier. With trees, it makes more sense because there is a root, and then we can kind of go deep. Whereas with a graph, there are cycles in it, so there's not really a good concept of depth. I guess in these terms, when we're going with depth first search, you can kind of visualize the graph as a tree. So if we have a tree, a depth first search is always going to go deep in its search before go deeper into the graph, whereas a breadth will go and visit all of the children of the top nodes first. It'll take a wider stance. So it's defined more in terms of trees for depth. Okay. All right, so answers B, as we saw before, for how we traverse that. Any other questions on that question, DFS or BFS, before we go on? Okay. So Dijkstra's. Dijkstra's algorithm, it's a way to find, given a source in a graph, a single node, what is the shortest path to every other single node in our graph. And the implementation of this is just like prims, which you guys should all be experts on after part A of project 4. There's very, very little differences between prims and Dijkstra's besides the data value that we store for each node. So there's a lot of nice similarities between the two. If you know a lot about prims, a lot of it can be applied to Dijkstra's as well. And the main thing to note about these are just the time complexities. They're just the same. We have a v-squared implementation if we use a linear search, just like with prims. But we can also implement it with a min heap like prims as well and get an E log v time complexity. So we'll start out with a quick practice question. Which of the following is false about Dijkstra's? A. Dijkstra's algorithm uses a greedy approach to solving its problem. Who can help me? It's true, yes. That was said on the last slide. So we have a set, just like with prims, a set of nodes that are in an inset and a set that are on the outset. And we choose what is going to be the next in node greedily by choosing the one with the lowest value. Dijkstra's algorithm cannot be used on an input graph with negative edges. This is an important little edge case with Dijkstra's that's not the case with prims or Kruskal's. We cannot be using Dijkstra's on any graph with a negative edge. So that's something tricky to watch out for. So that is true. C, it only finds the shortest path between two input vertices. This is our false one. for any starting vertex, it finds the shortest path between all vertices in the graph. Okay? So that's our false one right there. And just looking at the last one, it's capable of achieving a time complexity of E log v. That's true if we use our binary heap implementation. Okay. What algorithm family does Dijkstra's fall under? And does it produce an optimal solution? We just kind of mentioned this on the last slide. It's greedy. And it is optimal. Okay. So now we're going to walk through an example. So we have sort of our table here. And our question is, given that graph, what is the order of vertices that we add in to our set when we're performing Dijkstra's on this? And there's a quick hint. We should be able to quickly eliminate a couple of these from this, too. Looking at D and E, why can we ignore these? If we want to perform Dijkstra's on this to find the, yeah, exactly. Dijkstra is always given a single source. We'll visit every vertex in the graph and get us the path. So we can ignore those bottom two pretty easily. So starting with A, okay, we're going to look at the path to all of its neighbors. It only has C as a neighbor. Note this is a directed graph. So we can update that we have a path from A to C of 7. So we greedily add C into our set. So this is now an ini. And looking at C and all of its neighbors, C has an edge to B. And this is where it differs from prims, of course, is we're not adding 3. The edge from C to B is of weight 3. But we're going to be storing 10, because that's the total weight from the source, going A to C up to B. So that there is kind of the key difference with prims. And we're going to do the same thing with all of C's other neighbors, which includes D and F. So now we kind of have this table built up. And just like with prims, we greedily choose the next vertex with the lowest value. And in that case, we would have 9. And that would give us vertex D. So we do. That was a good question. The question was, do we store, when doing Dijkstra's, the previous node's value? Just like with prims, do we store the previous node? And do we store true or false? Okay, and to answer that question, so we do store true or false. We're kind of doing that right here with the colors of the vertices. So a vertex here is marked red if it's true, if it's in the set. And we can store the preceding vertex if we want the actual path. So right now at the end of this algorithm, we'll have the weights of the paths from one vertex to every other one. But if we want to get the actual path from which nodes we have to follow, then yes, we would want to store the preceding ones. So this is a directed graph. The question was, why is there's an edge from A to B that's 6? So it's directed from B to A. So we can't follow that. We've added A, C, and then we go to B because, well, it's the only route we have so far. So we want to make sure when we see a directed graph not to go in the wrong direction. Okay, so continuing with this example. We greedily choose from our inset A, C, and B the next lowest value, the next node which has the shortest path, which would be B with a value of 10. So we have A, C, B, I'm sorry, it would be D with a value of 9. So now we add D's only extra neighbor, F, that has a value of 11. Oh, hold on. Yes, sorry, we just did D. We added B, excuse me. So now we're at B. We update E because B has one neighbor of E. And we now get our weight of 15 by adding that edge weight from B to E of 5 to B's weight. We greedily choose our next one. We only have E and F as reachable vertexes, which are not yet visited. So we would go to F next. We'd be searching between these two here. F has the lower one, so we add that in. F has no new vertices that it's incident to, so we don't get to update any values. So our only option next would be to choose E. And then once we have E, we finally have a reachable path to G. So the E to G edge is of weight 4, so we would just add that in as our weight of getting to E of 15 plus 4, giving us a weight of 19. Okay. Were there any questions about the process of that? So like I said, it's pretty much like doing prims, except instead of just storing the weight of one single edge, it's going to be of the entire path from a source to the vertex. Okay. So these are just another example of Dijkstra's. I actually had these taken off on another set of slides. So we're going to go past these for time's sake. So if there's no more questions about Dijkstra's, we can go on to MSTs. So an MST, you guys should be familiar with these from Part A. It's a subgraph, given any graph. An MST is a subgraph that is a tree, and it's a tree meaning it's connected and acyclic, that has the minimum possible sum of edge weights. So we have our two algorithms for finding these prims. The important thing to note, since you guys are already so familiar with kind of how this works, is just noting down the two time complexities for its possible implementations. A good thing to have on your cheat sheet. A v squared with a linear search, or e log v if we use a binary heap to greedily choose our next vertex. Kruskal's, this is one we've had a little bit less practice with, but its implementation and time complexity is fairly simple to grasp. We essentially just sort the weights of all edges, and then just choose from that sorted list the next edge to add into our MST. And each time we add an edge to an MST, we check if it adds a cycle. If it does, we skip it and go on to the next one, and just continue doing that until all edges, until all vertices have been added to our MST. So that's where we get our time complexity of E log E. It's just the sorting of the edges. That's kind of the bounds on that. And a good thing to note, too, that's kind of useful, is that E log E is the same as E log V, because E will always be less than V squared. So whether E is around V squared or it's just around V, E log E and E log V can be equal. Okay, so a couple true or false questions on MSTs. If an MST does not contain some edge of the shortest length, then all edges of the graph must be the same length. So if we have an MST that does not include an edge that is one of the shortest lengths or shortest weights in it, must all of the edges of the graph be of the same weight? I see some yeses. I see some no's. This one's a little bit trickier. So this is actually false. So it is true that an MST must contain at least one of the smallest of the minimum weight edges of a graph. However, it is possible to, let me draw a quick example. So imagine this graph. Right here. So the minimum weight edge is 1 here. But to get a good MST, we can not include one of those edges. So it's not true that all edges inside the graph must be of the same weight, but just whichever ones are inside of this cycle. Question? I'm sorry, could you say it? Yes, it is. So the question's saying, if an MST does not contain some edge of the shortest length. So 1 is the shortest length. And a proper MST of this graph would look like this. It would ignore one of the edges of length 1. So in this case, it is fitting the problem description that MST does not include some edge of the shortest length. But it is not the case that all edges of the graph are the same length. Does that make sense? OK. So looking at the next question, if this graph is connected and has k vertices, an MST must contain exactly k minus 1 edges. OK, what's a property about an MST? It's a subgraph. A graph with v vertices. It's a subgraph containing, that is a tree.
It must be connected in a cyclic. So if it had more than k minus 1 edges, then we would have cyclic.
Yeah, very good. So if we had more than k minus 1 edges in our MST, then we must have a cycle in it. So that's just an important property about trees, is that a tree with v vertices must have exactly v minus 1 edges, because that's how many it takes to connect all of the vertices. And the addition of any extra edge would create a cycle. So for an MST of any graph, an MST is just a tree that contains all of those vertices. So that one is true. And now when implementing Prim's algorithm for a dense graph, using a heap is better than using linear search. So remember those time complexities. We have v squared for linear search and e log v for a heap implementation.
Linear search is better in this case because the binary heap implementation would give us complexity of v squared log v rather than v squared.
Yeah, absolutely. So that's just remembering the complexities between the two types. Remember, when it's dense, E is roughly equal to V squared. So V squared log V is not better than just V squared. It would actually be worse in the dense graph implementation. Yes, it is. The question was, is an MST a tree? It always is, yes. So it is a tree. An MST for a graph is a tree containing all vertices from the original graph. Yeah, so the question was, if it's not dense, would it go the other way around? So if this graph was sparse, then, so imagine if it's sparse, then we have E is roughly equal to V. So our heap implementation would give us V log V. So yes, V log V would be better than V squared. So good question. If the graph is sparse, then using prims with a binary heap is better than prims with a linear search. Okay. Another true-false one. So looking at this, prims and crystals will always return the same MST. Is this one true or false? It's false? Why? What can happen?
In the other example that you had of like a 2 and the cycle of 1, you can pick one of those 2 edges of 1.
Yeah.
Crossovers can pick one of them. Prims can pick the other.
Absolutely. So good answer. The key to that is that for a graph, it's possible for there to be many MSTs which are valid. So the one thing that we're guaranteed is that the MST weight will always be the same between the algorithms. So if prims returns an MST of weight 5, crystals will do the same. The actual MST could be different. So if you just imagine this simple graph here, all with edge weights 1, we can remove any 3 of those edges and have a valid MST. So there's no guarantee which one will be picked between the 2 algorithms. The next one, prim's algorithm will work for creating an MST even when the weights of the edges are negative. This one's a little trickier. I don't think we talked about this one as much, but MST algorithms work for negative edge weights, so that's no problem. That's a difference from Dijkstra's, which is important to note. But prims or crystals, it's fine with negative edge weights. C, an MST does not need to contain the shortest path between any 2 vertices. This one is, that is also the case. An MST is guaranteeing minimal connection between between the vertices. It's not guaranteeing shortest path. So oftentimes we can have very long paths between any 2 vertices. So that is true. It does not need to contain the shortest path. And then for D, we saw this with the last question. Prim's algorithm can run slower than V squared. That is the case if we use the binary heap implementation. Then we get a V squared log V, which can be slower. So the answer to this question is A. A is false. Of A? Yeah. So looking at an example of A, that is the one that I drew right up here. So the question was an example where they won't return the same MST. So in this one right here, looking at this graph, a valid MST for the graph is this, and so is this. Those are both the same. They both connect all the vertices, and they do so with a weight of 2. So there's no guarantee which edges prims or crystals will connect. So yeah, so they do work, even though they do work differently, their goal is the same. Their goal is no matter what, we'll always give you a minimum connection. So the final value of the MST, the final weight of the MST that prims gives you will always be the same as the final weight of the MST that crystals gives you. So that is the guarantee that they offer. It's just the edges won't always be the same. Okay, so the question was, when do we want to use prims over crystals? That just comes to the time complexities. So the time complexity for crystals is bounded by sorting the edges. So in a dense graph, that can be very expensive. If we have a lot of edges, if we have V squared edges, sorting that can be pretty heavy. So for that case, we want to use crystals on sparse graphs because then we're not sorting many things. So it's just a difference in time complexities.
But you could use the binary heap prims on a sparse graph as well.
Yeah, that's a good note. So the thing that was brought up is the binary heap implementation of prims gives the same time complexity as crystals, and it does. They're both E log E or E log V, same thing. So the difference in which one we would want to use on a sparse graph comes down to the constants. So even though they have the same time complexity, there's differences in what would actually run like when you write it on a machine. So
Can you give an example of B?
an example of what?
A negative edge weights graph with the MST works?
A negative MST. So this one's a little tricky, and I think the question was, how can we do it with negative edge weights? And I think it's with a modification of the MST algorithms.
You can't do it with negative edge weights.
If we add.
Even then, it doesn't work for you. You can't modify them all up. Oh,
Okay.
for Prims or crystals.
For Prims or crystals.
Oh, then it works.
Yeah. So
It doesn't work for.
Dijkstra's. Yes. So the MST algorithms, Prims and crystals, do work with negative edge weights, but with a small modification. And the trick is so say we have a graph where the lowest edge weight was -10, then we can add 11 to every single edge, okay? Perform the algorithm, and then subtract 11 again at the very end to get our valid MST. So it's a slight modification to Prims or crystals.
What you're saying is that you make everything positive, compute the MST, and then subtract away what you made it positive.
Yeah, so they technically work for negative edge weights, but with modifications. That's not the case with Dijkstra's, though, so we cannot do that the same. Why not with Dijkstra's? It's a good question, and I'm not sure of the answer to that one.
Involved. I would just know that for Dijkstra's, it doesn't work if it has a negative edge weights.
Yeah, so this is kind of going beyond exam stuff, but why doesn't Dijkstra's work? Why can't we just do that? I'm not sure. It's more involved. So just remember, we cannot use Dijkstra's with negative edge weights, whereas the MST algorithms, we can modify them slightly to work with negative edge weights. That might be more of something to look in CLRS for. I can't say. I'm not familiar with that section, but I think it's worthwhile knowing it's only a small modification, just adding to make all the edges.
Like, if you're adding 11 to every single edge, wouldn't you need to subtract 11 more than 1 at the end?
Yeah. So I'm saying, yes, it would be. So at the end, we would subtract whatever we added times the number of edges to get that. Yeah. Yes. Okay. I don't want to spend too much more time on the negative edge weights with MSTs because it's not something we focus on too much. So if there's any other questions about MSTs. Okay. So let's look at the new question. This is a good one. So it's kind of a lot to read there, but the question that they're asking is this is someone's attempt at making an MST right here, represented in this adjacency matrix. And we want to find out that given this information, given that adjacency matrix right there, is that a valid solution for an MST? So in these kinds of questions, just like before when we saw the adjacency matrix on the DFS-BFS problem, it's really helpful to draw these out. Because just looking at an adjacency matrix and trying to figure out if it contains a cycle or is minimal is very tough. So we'll start with A. We'll draw all of its neighbors. Okay. B contains no neighbors, so that was A done. B contains no new neighbors. C contains no new ones. D has a neighbor of F and G. Okay. E, let's see. E is a neighbor of G, so we can draw E right here. F is a neighbor, has D and G, so we just have to draw this new edge right here. And stopping right there, we can kind of immediately see our problem. So in an MST, what's the guarantee about an MST? It's acyclic. It's a tree. So when just taking this, see, that's where kind of drawing these out can kind of help a lot. Trying to spot a cycle on this adjacency matrix can be tough. So, but we can see between D, F, and G, this cannot be a valid MST because we have a cycle. We can achieve a lower weight by removing one of these edges. A Hamiltonian cycle is just a cycle in a graph that contains all of the vertices in that graph. So think of like a traveling salesman type cycle. So looking at the actual responses to this question, the correct one is no, because the graph contains a cycle. A is not true because it is fully connected. That is a property that we do need of an MST, that it is fully connected. This one here about it not being minimal, so is not something that's not a reason we can deduce why it's invalid, because there's not like enough information. The adjacency matrix they gave us was an attempt at an MST, so we don't know any other edges in the actual network. And looking at C, that's just if a tree does contain a Hamiltonian cycle, then that's a concern. It should not. Okay. So we have our correct answer is D. It should not contain a cycle. Any questions about that one? Okay. So looking at this one, this will be a common theme you'll kind of see, is given an adjacency list or an adjacency matrix, do one of our graph algorithms on it. In this case, we have an adjacency matrix, and we want to run prims to try to figure out the order of the vertices that are added into the MST. So we're starting at vertex 0, and we should be familiar with this. In this case, it can also be helpful to kind of draw it out, but adjacency matrices lend themselves well to prims. So we're going to greedily choose the lowest weight edge that we've looked at. In that case, this is 1. So the next vertex we're going to add to our MST will be 4, this edge from 0 to 4. Okay. So we're going to be marking all vertices inside of our MST in red here. So now we have 0 and 4 inside of our MST. And now we also want to now consider 4's edges to its neighbors. So we have these new edges to consider, 22, 5, and 13. Notice we're ignoring 1 because this edge weight here of 1 just goes back to 0, which is already in the MST. So looking at all of these edge weights that we will consider, 4 is the lowest. So now we're going to add the edge from 0 to 1 into that MST. So now we have an MST containing 0, 1, and 4. Okay? So now we also want to consider 1's neighbors, okay, to all of its edges to vertices not in the MST. So we're considering those. Can anyone identify the next vertex that we would add into our set? The next one in the MST? 2? Yes, that is. So we would now consider the edge from 1 to 2 is the lowest among all of these. So we add 1 and 2. And obviously the last one here we're going to add in is 3 because that's the only vertex left. And looking inside of its column, all of the other vertices have been added. So the actual edge will be the lowest weight, 7 here, going from 2 to 3. So that will be our final answer.
I don't understand how, like, where you translate what you just did to, like, I guess when I do prims, I picture, like, the table method that we did last year.
Yeah.
So, like, I guess I just can't follow this without.
So I think, yeah, it can help a lot more, especially because we do only have 5 vertices here. So on an exam question like this, when you are given an adjacency list or an adjacency matrix, it can be very helpful to draw out the prims table and just kind of do it by hand translating there. But the main thing that we're looking for here is you just want to so given this, with prims, the idea is still the same. We mark things that are inside of our MST, and then what we want to do is consider among which of these has the lowest edge from 0 or 4 to one of these. Okay? So it's sort of the same idea, whereas in our prims table we would be looking in that linear fashion. With here, we're just going to consider what's the lowest weight edge from any of these, from the innie set to the outie set. So if it does make it easier to read, it's worthwhile, just like drawing the graph on the DFS problem, to draw out a Prim's table. OK. And that's all I have for you for MSTs. So if there's any last questions, I can take them. But if not, then we'll go to Jake to cover algorithm families.
Oh yeah, the old one, sorry. Forgot about that.
Hey, Paul? Paul? Turned off.
Hear me? Good, good. Okay, so real quick, I don't have a whole lot of slides for algorithm families, so this is going to be just a super high-level summary of a lot of the different types of algorithms that you guys have learned up to now. So please stop and ask me questions if you have any. So first, brute force. This is basically the most naive of all of the algorithm families. This is just, we're going to look at every possible permutation of the inputs. And this is guaranteed to give us the optimal solution, right? If we look at everything, we will leave no stone unturned. And so then obviously brute force is the most inefficient, right? Because it's computationally expensive to look at every possible permutation of inputs. Greedy algorithms are algorithms that are typically very fast. This is the main advantage, but they're not guaranteed to return an optimal solution, right? So we're basically sacrificing guaranteeing an optimal solution for speed. So most greedy algorithms, they make locally optimal decisions with the intent that it will lead to a globally optimal solution, but that's not a guarantee. Questions on greedy algorithms? Nope. Okay. Divide and conquer, these are pretty specific. So I know you guys have seen quick sort and merge sort are examples because these are two of the only examples, at least that I can think of. But basically, it's just we have some sort of problem that can be divided into smaller subproblems of the same category. And then the difference between this and dynamic programming, which we'll see in the next slide, is that often with divide and conquer, you don't end up duplicating any of the work, meaning that the subproblems do not overlap. If they do overlap, then dynamic programming is probably going to be your best bet. So we have this bullet here, often looks like divide and conquer, but the subproblems are not distinct, meaning that some of the work is repeated. And then we have a whole section on DP, so this is covered in a lot more detail later. But just to recap, high-level summary, It's typically faster if you're able to use dynamic programming than doing an analogous solution that is not dynamic programming. And there is always some additional memory overhead for doing so. So in order to store every subproblem that you solve along the way, you need typically a one-dimensional, two-dimensional vector, something like that, just where you track all of the work that you've done. Questions on DP? Okay. And so then backtracking and branch and bound. So I suspect the reason that we have these two together here is because it's often the case that students get these two confused or conflated, and that's understandable. So just anytime that you hear backtracking, think constraint satisfaction. Anything that you hear branch and bound, think of optimization. So if I give you, if I say I want you to do part C of your project, but I say don't find me the optimal tour, find me a tour that is below some weight that I give you. There could potentially be many solutions to that problem, right? That's a constraint that I've imposed, and backtracking would then be your best bet, right? Because you don't have to return. I'm not saying return to me the tour of lowest weight. I'm saying the tour that's below some threshold that I give you, right? So that's an example of a constraint satisfaction problem, whereas branch and bound has to do with optimality. Branch and bound is like an improved version of brute force, where we have some measured way or some estimate of permutations that we do want to explore and do not want to explore. But we're still looking for the optimal solution with branch and bound, and this is not a guarantee for backtracking. Does that make sense, the difference between the two? So this is just more of the same. Backtracking. Oh, hey, we spelled it wrong. Look at that. What choices should I make to satisfy some constraints? And branch and bound, what choices should I make to obtain the best or optimal solution? So this is, again, reiterating. Any solution within a constraint would be backtracking, and then the best solution has to be branch and bound, right? It could be the case that the constraints that I give you for a backtracking problem are so severe, so tight, that the only possible solution is the optimal solution, at which point these two algorithms would be solving the same problem, but that does not have to be the case, right? It's possible, but it's not a guarantee, or it's not a requirement, I should say. Questions so far? Okay, so then this is pseudocode for backtracking. Basically, we just want to permute all of the inputs. So if the current V, I guess V is some node, if it satisfies whatever constraint is given in the problem statement, we check if the current V or the current vertex is a solution, and if it is, we return the solution. And then otherwise, if it's not a solution, but it still satisfies the constraint that I'm given, then let's go ahead and check every node adjacent to V, the current vertex. Make sense? Okay, and so then branch and bound pseudocode, you should all be pretty familiar with this. A lot of the same in terms of structure, except slightly different checks going on here. So we first check if the input node is a solution, and then if it is a solution, we check to see if we should update our best so far, because remember, we're looking for the optimal solution. And otherwise, if the best possible, so this is the bound right here, right? This is our estimate. If the best possible score from the current vertex is greater than the best, it doesn't have to be greater than, obviously. This can be less than the best if you're solving a minimization problem. It looks like in this example, we're going for a maximization problem, but it doesn't really matter. But anyways, if the best possible score is better than the best, then for every child node of the current vertex, we make a recursive call on the child and then make all the same checks again, same exact function. Question? Sorry? What about pruning? What do you mean? Right, so if this is false, we don't explore anything, right? If we don't enter that if statement here, yeah? Any other questions? Okay. We'll do an example problem. Take a couple minutes to look over this and then tell me what you guys think, if any of these are immediately true or false. check option D. 1, 2, and 3? Oh, 1, 2, and 2? Yeah. Seems like a problem, huh? Yay. Now it makes sense. Woo. Answer C, by the way. But let's talk about it. What do we think? Why is it 1 and 2? Did anyone get C? Did anyone think 1 and 2 were false and 3 was true? You don't even have to give me why it's 1 and 2. Just for any of these 3. Why is 1 false? Why is 2 false? Or why is 3 true? Yep. Yeah, that's right. So typically, when you're using branch and bound, you're either solving a minimization problem or a maximization problem. If it is a minimization problem, then you're typically going to have some lower bound estimate, right? And vice versa, if it's a maximization problem, you'll have some upper bound estimate. But to put it in the context of something that you guys are familiar with, you didn't have to, in part C, opt TSP of Project 4, you didn't have to start with your fast TSP as your upper bound. That was really just something that you did so that you had a better starting point than infinity, right? So it's not a requirement, and in fact, the two will often be mutually exclusive. You'll typically only be using one or the other in a branch and bound problem. So yeah, 1 is false. Why is 2 false, and why is 3 true? Or why is 3 true, if you want to guess either. Yeah?
First one, it says effectively use branch and bound. So if it's faster, isn't it more effective?
In order to effectively use, you can make that argument, but it's not a requirement for you to effectively use branch and bound. I'm sorry? Okay, sure. So you provided me with an example, but that does not generalize. I could give you one counter example to this, right? Yeah, do you guys have other questions on that before we talk about 2 and 3? Yeah, maybe it's poorly worded. Maybe it could be worded better, sure. I don't disagree with that. Yeah, let's move on though to 2 and 3. What do we think? Why is 2 false? Why is 3 true? Yeah.
So for number 2, the minimization problem, if your lower bound is too large, then you can prove potentially correct solutions.
Yeah, that's pretty much it. Nothing too tricky there. You guys might have been familiar with that because you might have experienced it in the last part of Project 4, right? So you want it to be as large as possible without going over what the true, global optimal is, right? So yeah, that's why 2 is false. And then why is 3 true? Yep. So if your bound or your estimate function is no better than doing this, then your problem is, or your implementation is no better than a brute force solution, right? So yeah, nothing too complicated with that one either. It's basically just the point of branch and bound is that we are using what we know to improve a brute force solution, right? So when I say improve, I mean in terms of runtime by potentially eliminating one or many search spaces, right? So if doing branch and bound gives you a solution that's no better than brute force in terms of everything that you search or in terms of the time that it takes, then it's not going to be very effective because the whole point is that it has to be an improvement, yeah? Yeah, question?
Should be as large. Well, no, because then it would be an upper bound estimate. You would not be doing a lower bound estimate in a maximization problem.
Like, wouldn't you update the lower bound too?
What do you mean? Update the lower bound?
Wouldn't the lower bound be like updated to reach like the next highest value every time?
Yeah, but I wouldn't call it a lower bound. I would call it your best so far, right?
But isn't like wasn't your upper bound like the best so far for a minimization problem?
Isn't your upper bound the best so far? Yeah, sure. Yeah, question.
To be clear about terminology, when you say a lower bound, it means that your solution must be larger than your lower bound, right?
Can you repeat that? I'm sorry.
Yeah. When you say lower bound, does your solution have to be bigger than your lower bound and smaller than your upper bound?
When you say your solution, do you mean like in the context of TSP, like your best path so far?
Yeah.
Then yes, it does have to be. Because if your lower bound is greater than your best so far, or your best so far is less than your lower bound, then something is wrong. The point is that it's supposed to get you as good of an estimate to the optimal without actually going over the optimal, right? So yes, to answer your question, yeah. Anything else? Okay, cool.
Can everybody hear me?
It's on.
It goes all the way
Wait, okay, it's on. Okay, let's talk about some knapsack problems. For a knapsack, there are like a few algorithms that we can use. Brute force, apparently, and then greedy, dynamic programming, backtracking, and branch and bound. And some of those are optimal, some of those are not, and we'll talk about the complexities and if they're optimal. So apparently for brute force, the complexity is just n times 2 to the n, and it's optimal because you just go through every possible solution and until you find the best one. So it's exhausted. That's why it's optimal. For greedy, for a normal knapsack, it's not optimal, but for some versions of knapsack, it's going to be optimal. And because it's greedy, they're just taking either the largest value item or the largest ratio or any definition you define yourself. So it's gonna just be open because you're just gonna go through elements. And then for dynamic programming, you're gonna have a table of n times n as being in elements and c in case of capacity. That 2D vector, that 2D vector will not be filled. Not all elements will be filled, but you will have to have that n times c 2D vector to do this. And it requires integer weights because we use the integer weights as the indexing into that 2D vector. It's okay to have float or double weights. It's going to be really space inefficient, and that kind of makes you don't want to do that in programming anyway. And for backtracking, it's just adding the constraint to it. It doesn't really work that well, or it doesn't really quite fit into, itself doesn't really solve the problem. For branch and bound, you use the initial estimate of best solution as a lower bound, and also as you progress, you will record your current best as the lower bound. And then to estimate the upper bound to get estimate the remaining value of the partial solution to get the upper bound and compare that upper bound with the lower bound to see if the current knapsack solution is promising and worth keep going. So let's take a look at the practice questions. So anyone wants to answer this question? Yes? Yeah, so as we said before, for dynamic programming approach, let's take a look. So based on this slides, the fastest way we can use for integer weight knapsack problems is dynamic programming, which the complexity is going to be just n times c, n as being n elements, and c as being capacity. And here we have x minutes, which is basically the capacity, and n writes here would be the n elements. So that will be n times x, which is going to be b. Any questions? Yes. The overlapping problem, you mean specific for this one or for knapsack? Okay. This is going to be if you, back to this. So when you choose to do n minus 1 writes, those writes you have, either you're going to do the next write and minus sometimes, some minutes you have, or don't do that write and still have those minutes. Does that make sense? Okay. Any questions? Okay. So this question.
What do you mean by for? Some can be solved easily and others are much harder.
It's just, as we said, as we know that we have several versions of knapsack covered in lecture, I believe. So there's like a normal knapsack. You can just only take the whole item or don't take the item, or you can take a fraction of the items, or either you have integer values weights or like fractional, doubles or floats. Those are different versions of knapsacks. Okay, anyone wants to answer this question? You don't have to give your opinions on all four. You can just talk about whichever one you're confident about. Okay. Yeah. Yes. So one is true because we know N and M are both integers, and then we can use DP. And then because of DP, runtime is just N times C. In this case, it would just be M times N. Anybody? Yes? Next. Yeah. Because, so, do you know why we have N times C as the complexity? Because we have the 2D vector, right? And in that 2D vector, one dimension would be, let's say you have capacity of 5, you have 1, 2, 3, 4, 5. Like if you have double or floats, you are not going to have those. More questions? Yeah? Yes. Well, like if you want, you can still use DP for not ends, but it's like not time efficient. I mean, space or time efficient anymore. So it's not worth doing that, and it's not going to be n times n. Okay. Next, somebody said, yeah. Yes, sort of. DP will give the optimal. It's not suitable for branch and bound because itself is not just an estimate. It would just loop through basically all the possible solutions in a quicker way than the brute force. So it's not an estimate function for branch and bound. Yes? Yes. So one of the good function to do this estimate for branch and bound would be just greedy. So you will basically take the ratio of the values over weights and sort that from the largest to lowest, and then take all the whole items that you can take, and then take the fractional of like whatever you can fit in, and that will be the best, probably the best upper bound you can get. Any questions? Okay. Anybody wants to answer 3? Okay, for 3, it's a bit weird. So for branch and bound, basically, if we say we're using branch and bound, you're just doing brute force because other ways are just following that specific way. So branch and bound is a way to improve over brute force, and the time complexity for brute force we're saying is just n times 2 to the n. And since branch bound we cannot promise that we can actually improve on brute force, we will only say that it's theta of n times 2 to the n. Like it's solely based on your promising function to see how you can improve, and there's no guarantee. So the safest way would just be to say that it's theta n to the 2 to the n. Yes? Brute force is n times 2 to the n. Do you know why it's n times 2 to the n? So 2 to the n is because you have to loop through every possible state of the whole knapsack, and n is because you have to calculate the weights and the values, so you have to sum up the n elements you have. That's O of n. So you have a for loop from 1 to 2 to the n, and then inside that for loop you have O of n loop to decide the values and weights for that specific choice. Oops. Okay. I can see that 4 is also true. More specifically, the fractional knapsack is the easiest because it can be solved by greedy. Since you can just take a fractional of everything, you can just you can just start from the largest and take until you cannot take. And second version, we talk about the integers. So integer weights, integer values of the knapsack, it can be solved by DP, which is still a P difficulty problem. That's still like easier than the float or double weights or values knapsack, which can only be solved by brute force plus branch and bound. So you have to take the n times 2 to the n approach. Any questions? Yeah.
Well, the question states that M and n are both integers.
Yeah.
Of all the versions of the knapsack prong where m and n are integers, then which ones are harder and which ones are easier? Because the double version isn't right in this version. Because the column says m and n are both integers.
Oh, I think the fourth choice is not kind of related to the statement. It's just by itself. And I don't remember exactly how many versions do we have by the when we only have n and m as integers. I think there's just only one, or fractional. So if you have n and m are both integers, you can still have fractional and you can still use greedy. If n and m are not integers and it's fractional, you can still use greedy. So by fractional, it's fractional knapsack. No matter what m and n's are, it's still the easiest. And then m and n as integers are the second easiest, and the other versions will be harder and may goes into the NP hard part. Any questions? Okay, and then Faye.
Oh, great.
Can anyone hear me? No. Let's try.
Now. There we go. Okay. Wonderful. All right, so let's get started with dynamic programming. Essentially, we're going to use it anytime we have something that has a smaller shared or common subproblem, right? So the basic idea is that we have one big problem, and we can break it up into smaller subproblems that have the same kind of general input or general format, but then we end up having to run some of those subproblems over and over again. So rather than running them over and over again, instead we're going to run that once, store that kind of return value in memory somewhere, and then we'll just go look at that memory value when we need to go run that subproblem again. So rather than rerunning parts, we're just going to go ahead, store them in memory, and then look there. So we're using extra memory to speed up. We can approach dynamic programming in two ways, right? We can either do top-down or bottom-up. Both of those are going to involve some sort of a memo vector, or something where we're going to store those values of the smaller subproblems. So if we want to do a top-down dynamic programming approach, we can just essentially write a recursive function and then add in one extra check. So we say, here's our base case. Here, now after the base case, I'm just going to check, have I already done this specific problem before? If so, I'm just going to return that value. Otherwise, I'm going to go ahead, finish that problem, and store it in my memo vector. So that then next time when I run that problem, when I have that check, have I run this before, I can say yes, go grab that value, and then I'm good to go there. Otherwise, we can also do it bottom up, where essentially instead of kind of filling the memo vector whenever we finish a problem, we're just going to go ahead and fill the memo vector starting at our base case and then looping through it and filling in every single value that we need. So in this case, we're basically just going to build up that memo vector ourselves, and then we just stop when we get to the input that we're trying to compute. To solve them, we can kind of think of it as a couple of different steps, or some things that we want to keep in mind as we work through a dynamic problem, or a dynamic programming problem. The first thing we want to do is come up with some sort of a subproblem. And we want to think of that as a what, not a how. So for example, we want to think of, if our total problem is the maximum number of ways that I can tile something, we'll get to that, then our subproblem should have that same format, right? I don't want to think of it in terms of, okay, I just solved this problem, what is it going to impact later on? I want to think of, what do I already have computed so that I can compute this specific subproblem that I'm at? Does that make sense? Kind of? So I like to think of it like, for example, if I'm looking at this example of a problem, right? Rather than thinking, okay, I have this, I start off with like this 2x1 blue tile. Then, okay, from there I could add on a yellow, and then I could add on another blue, or I could add on a yellow, and then I could add on 2 reds. So rather than starting at 1 and trying to think of all of the things that could impact down the line, I want to just think of it as like, okay, if I am at a scenario, like if I'm at this specific scenario right here, where I have a blue and then a yellow and then a blue, how did I get to that scenario specifically? So rather than trying to think of like one starting point and branching out from there, we're trying to just kind of like pull everything together into one specific subproblem. Then once we have that kind of setup worked out, then we want to figure out our recurrence relation, right? So when we have our recurrence relation, we just want to figure out what the base case for that is going to be, and then our recurrence. So essentially, like, what base cases do I need to have filled so that when I go to look for them, I'm not like going out of the bounds of my array or something like that. Essentially, what base info do I need? And then after that, for everything else, what is the relationship that I can look at? And then once we have that, we can essentially implement it either bottom up or top down, because we can either do it top down, where we just put in our base cases, put in our check, recurrence relation, store it in the memo vector, or we can do it bottom up, where we fill in all our base cases first into that memo vector, and then we can just go ahead and loop through it, filling in every other element in there, every other space in our memo vector. Any questions on the kind of like big approach to it? Yeah. Yeah. So this is great, actually. What would be our base case here? Does anyone else want to take a shot at that? Or first, let's read the problem. That would probably help. So how many ways are there to tile a 2x(n) grid with the below tiles? So we have a vertical 2x1 blue. Then we have a yellow kind of like 2x2 square, or a horizontal 1x2 red. So if we think about our base cases, I usually like to think of it, like usually your base cases are going to be somewhere in like the 0, 1 range, something like that. If you're filling your memo vector, you can usually think of it as it's going to be somewhere along your edges, because you want to make sure not to go out of bounds of the vector. And so if we think about it here, what are some potential base cases we could think of? Or even just if we start building up the problem, right? When n is equal to 1, exactly. So when n is equal to 1, how many versions, or like how many ways can we tile? Only one way, right? We can only use this one. How about when n is equal to 2? 3 ways, right? We could do it either with 1 of these yellows, 2 of the reds, or 2 of the blues. Then there's one more that we need. So we have 1 and 2, those are kind of like our base cases. We need one more. So let's say that I'm trying to figure out how many ways to tile like a 2x2 or something like that. If I'm trying to think of previous problems, so I have my 2x1, right? I have when n is equal to 1. What other potential subproblem might there be? I heard it whispered somewhere. Shout it out. 0. Okay, when n is equal to 0, right? So how many different ways are there to tile 0? Technically 1, actually, right? So there's like one way to tile 0. We can also kind of think of it in terms of thinking about that recurrence relation, right? So now that we have those base cases set up, we can think of it, or we can start to think of how that recurrence relation might be set up. So if we think about, for example, like, let's start with n equals 4, and then we'll kind of reverse apply it to get to n equals 0 gives us 1. So let's say that we have n equals 4. Then we have these 11 possible options for how to tile these. What can we notice about all of these options? Or how can we think about building them up? Yeah? Right, so we can use subproblems when n equals 2 and n equals 1. How did you come up with 2 and 1? Exactly, right. So if we take a look at these problems, we can kind of see, like, for example, this problem I could have built up by just adding on this blue one to the left, right? So that's the same as saying, okay, how many different ways could I tile this 2x3, and then I'm just going to add in that one. But on the other hand, I could also always be tiling it, you know, with these two red ones, or with this yellow one. So what we can kind of do is we can break it up visually to say, so f of n is going to be the number of tilings on a 2x(n) grid. Then we have our base cases. And then now we're going to split the tilings into categories. So this is kind of where, do you all remember in lab when we talked about kind of take it or leave it, that type of thing? So this is a very similar approach. So what we're saying is, okay, in order to get to this final approach, usually I have my base or my sub case, right? And then I have one extra thing that I'm doing to it. So in this case, I have a sub problem, and then I'm always adding in a certain type of tile or a certain number of tiles, right? So for example, if we think about it this way, for all of these top versions, I'm always adding a 2x1 blue onto it from the left. So we can break all of those up now into, okay, how many different ways can I tile it if it's n equal to 3? Any of those I can then add this blue, you know, tile to, and then I can get to this final subproblem of n equals 4. So I want to figure out how many times I can tile it with n minus 1, and then I'm going to kind of consider that that's an entire grouping. But then I could also, alternatively, right, I could add 2 reds, or I could add 1 2x2 yellow. So in that case, right, then my question becomes, so I can either add 1 blue, or I can add 1 yellow, or I can add 2 reds. And then if I'm adding a yellow or a red, I'm figuring out how many ways could I tile a 2x2. Does that make sense? So we're always kind of adding, at this stage, right, when we're thinking about n equals 4, what we're thinking about is, okay, I'm going to add kind of like this last step onto a previous subproblem. What previous subproblems am I looking at to add that last step onto? So in that case, our last steps are going to be these 3 tiles, or these 3 tile arrangements, and then our previous subproblems are going to be what we add on to get a total of n equals 4. And so if we want to write this out as the total recurrence relation, what would that look like? So if I have f of n is the number of tilings on a 2x(n) grid, how could I write that out recursively here? So we know we have to do something with our n minus 1 and n minus 2, right? Okay, what am I doing with those? Adding them up, right? Okay, so I've got n minus 1. And then what am I adding to that? 2 times f of n minus 2, right? Because both of these are the same n minus 2s, right? We're just adding a different set to the left-hand side of them. So it's the same problem. We're just saying now we have 2 potential ways to kind of like add on to there. Awesome. It's going to be the same thing. Great. So now when we want to write so now we can kind of look back at why we ended up with f of 0 is equal to 1. So if we take a look, if we want f of 2 to be equal to 3, then we need it to be equal to f of n minus 1, right? So that's going to be f of 1 plus 2 times f of n minus 2. So that would be 2 times 1 plus 1 to get us to 3. So in that case, sometimes you want to just play around with like really small portions of it to make sure that you get those base cases right. Yeah, so that's just something where I would recommend like writing out a couple of the first few and then trying to see if there's a pattern that you can see and thinking, you know, which of these are enough for my base case. You know, once I start to see the pattern, what's the first one I can start that pattern at? Okay, awesome. Any questions on the recurrence relation? All right, ready to write it as like an actual DP? Yes, okay, great. So we've got our recurrence relation. So then now we're going to basically do it bottom up. So what we need to do is we need to start off with our memo vector, right? So that's going to be just, in our case, we're just saying it's the max between 2 or n plus 1. And the reason that we're doing this max right here in terms of size is just if we have something where it's like n equals 0 or something like that, we still want to just be sure to always code in our base cases. So if we guarantee that we have enough space for our base cases, then we don't need to worry about checking for that when we're filling in our base cases. We can just assume we have that amount of size and fill it in. So we have our answer at 0 is going to be 1, so f of 0 is 1, f of 1 is 1, and then we are just going to loop through and fill in our table, right? So we're saying for each case after that, it's just our recurrence relation. So we have answer at I is equal to answer at I minus 1 plus answer at I minus 2 plus answer at I minus 2. And that's essentially all that we have, right? We're just going to go through and we're going to fill it up. And then by the end, we're going to have, like let's say that our n was equal to 4, then we're going to have for n equals 0, 1, 2, 3, 4. And then in this case, remember we need to kind of like revert back to 1 indexing. So we want to return at n. And that's why we reserved size of n plus 1 beforehand, so that we could include that 0 case. Good? What questions do you have? If I build it up bottom up, am I guaranteed to always have my solution at answer n? Oh, yes?
So in this case, when n is equal to 2, that's not a base case.
Right, so in this case, when n is equal to 2, it's not a base case. You can always code in more values if you want. Like you don't have to just code in your base cases. For me, it's like for example, if I was feeling like a little shaky on whether or not 2 was a base case, I'd just hard code it in. But sometimes just building them up can help you see like how many of them are your base cases, because once we get to f of 2, we can see that our other recurrence relation holds. So then we know that like, oh, from 2 onwards, we can just use the recurrence relation. Yeah, good question. Yeah. Yeah, so in this case, it's not a recursive function, but it does have a recurrence relation. So that's a great question. Let's say that we wanted to write this as the recursive function itself, right? Because in here, right here, this is going to be our recursive call, so to speak. But when we're doing it recursively, instead of calling another function, all we're doing is looking at a previous value that we've computed. So that's kind of like what we could consider the return value of a recursive function call that we would have done. So you can think of like all of the little, like everything in the vector is the return of what could have been a recursive function call if we had written it recursively. Yes, exactly. This is bottom up. Yes?
It looks like some of these questions where you can write it as a recursive function are very good for 1D vector kind of thing.
Yeah.
It seems like in lab 10, we did 2D vectors, and that was, I wouldn't even know where to start with a recursive version of that. So is that like a good sign, like a good way of telling whether or not you should be using 1D or 2D?
Yeah, so any one that you can do with, I usually start to think of whether to use 1D or 2D with the number of parameters that I'm passing in, or the number of parameters in my recursive call, right? So in lab, when we had lab 10, right, we were thinking not just of like one singular n, right? We were thinking of like the number of meals and the number of punches. So in that case, when we had a recursive call, or when we were thinking of a subproblem, that subproblem depended on the number of meals and the number of punches left, so that's why we had that as a 2-dimensional vector. So in that case, when we write something for lab 10, when we write a recurrence relation, it's going to be something of the form like T of MP, and so that's usually a pretty good hint that you should be using a 2D vector. The other thing on the exam specifically that will be a big hint is your memory complexity. Right? So in a DP problem, what is my memory complexity? Or what is it equal to? N times m, right? If we have a 2D memo vector of n times m. So our recursive, or a dynamic programming problem will have the memory complexity of its memo vector, essentially. Because we can always write it as bottom up, just filling in that memo vector. So if we tell you something that like the size complexity or the time complexity of this should be nm, then chances are that means you're filling an n by m vector. But if we say that your size and memory complexity should be O of n, then that's a big hint that it's going to be a 1-dimensional vector of size n. Yeah? Yes? Yeah, so in this case, we're adding I minus 2 because we have 2 ways to add on to that. So we could either have So we have all of these for I-2, right? I-2, we have these 3 ways of doing it. And then to get to our total of n equals 4, we can either add the yellow 2x2, or we can add the 2 reds stacked on top of each other. So we're saying there are 2 different ways that we can get there. So we're essentially just saying, like, one of these is when we're adding the red, and one of them is when we're adding the yellow. Okay. Great. So going back to that question of, are you always guaranteed to have your final answer at the last location? The answer to that would be no, right? If we think about Lab 10 and what we had to do in Lab 10, or have to do in Lab 10, it's not guaranteed to be in that last location of your 2-dimensional memo vector, right? Because it depends on what that vector is representing as a subproblem, right? In the case of lab, right, where we have meals and punches, then when we have our, nth meal, and we have from 0 to 5 punches, right, all that this is representing, right, is that I end on my nth meal with 0 punches versus I end with my nth meal with 1 punch, 2, 3, 4, 5 punches. So when we're trying to figure out where the correct solution is located, it might not necessarily be that I end my nth meal with 5 punches. My ideal solution might have been somewhere else there. And so that's another thing that you always want to kind of think about with a DP problem. At the end is just, where is my final solution located? Is it really just that last element? Do I have to do a min or a max between 2 elements? That sort of a thing. It's just always like a good final check to have. Okay. Yes?
For problems like this, since like the frame is always going to be like 3, like n minus 1, minus 2, couldn't you make, or like the memory complexity, could you like reduce it to constant, so it like wouldn't need to store everything in a bottom of approach?
So in this case, you're saying because we're kind of like always overwriting, so we could just hold on to those 2 values of n minus 1 and n minus 2? Yes. So that is something that we could optimize in that way. In this case, we're kind of like showing it the whole way through, because usually it's easier to go from like the entire filled vector down to those 2 elements rather than trying to like build up an understanding of DP from the 2 elements to the larger. But you're correct, right? If we notice that in this case we're always just going to be holding on to those 2 elements, and we're going, each element one after the other, then we can just hold on to those 2 values and kind of like overwrite them as we keep filling. Yeah. Other questions? Okay. I would recommend for DP just like finding some practice problems and working through them. There are a lot of practice problems available online, and for me, like the hardest part of a DP problem is trying to figure out the recurrence relation. And the more practice you have with DP problems, the easier it's going to be to see that recurrence relation. Because a lot of them do start to have patterns, and once you start to identify those patterns, it's easier to see them in the exam when you're given a problem. And for me, like if top-down makes more sense to you, then just like lock in that top-down. And if bottom-up makes more sense, then like roll through that. Okay. How much time do I have left? I have 5 minutes. Okay, real quick, we've got 2 multiple choice questions, so we'll go through those really quickly, and then we will be done. All right, so in this case, we have the function bicoefficient, which is going to compute the binomial coefficient and choose m. If we adapt binomial coefficient to use dynamic programming while continuing to use a top-down approach, what does the memory complexity of binomial coefficient become? So where does the space complexity of a dynamic programming problem come from? Yeah. The parameters, right? Exactly. It comes from the size of our vector, right? So in this case, what is going to be the size of our vector? N by m, exactly. So that means that our space complexity is going to be O of n by m, because that's going to be the size of that vector that we're adding on. Awesome. How about this one? Which of the following statements about dynamic programming is true? Let's go through them. We'll go through them one by one. So someone talk to me about A. The top-down approach is always more efficient than the bottom-up approach. True or false? False. And why? They might be the same, right? It's not guaranteed to always be better. If you still need to hit every single, element of your matrix, then top-down is going to have the same complexity as bottom-up. Awesome. How about B? The bottom-up approach can be used anytime the top-down approach can be used. True, right? In those cases, we have the same recurrence relation. As long as we have that space of memory, we can go ahead and use it either way. Yes? Vice versa, can top-down be used anytime bottom-up can be used? I believe that's true. There are certain cases where it might be less efficient, or so where one might be less efficient than the other. Like for example, if your top-down approach is going to hit like log n of your potential cases, like all of the possible scenarios, then that would be more efficient, because in bottom-up you'd still have to fill every single spot. But they both can be used interchangeably. Yeah. How about C? Dynamic programming is useful when a problem divides into independent subproblems. False, right? The whole point of DP is that we're using overlapping subproblems, right? So we're not recalculating everything. How about D? When applying dynamic programming, the same subproblem is solved multiple times. No, right? So we're not solving it multiple times, we're solving it once, but we might go look at that result multiple times. Awesome. Pro tips, right? Just you want to look for that recursive solution, figure out how many inputs there are, and then just use that saved info. All right, awesome. Good luck on the exam. We have practice questions at the end of these slides that are posted, so feel free to work through those. We'll have office hours. Good luck. And we'll stick around and answer questions, yeah? Yes.
So like for the DP problems, if we care about two things, like when we do the recursion call,
yeah.
If we pass in two parameters, is that means like the memory will be like a 2D vector?
Yep, exactly.
So that's pretty much the way we distinguish from 1D to 2D.
Yeah.
Just like either we're passing 1 or 2.
Exactly, exactly. Okay. Or sometimes there might be something where you might start out with a 2D and then you notice that like, oh, I'm always just using one value from this column or something like that. And then you can like collapse it down to a one-dimensional vector or something like that. But usually if you're passing around two parameters, you'll have a two-dimensional